Oh.
Nice, guys. Nice. Okay. Today's lesson, I hope, feels like review for you guys. Did you all hear me on this? All right. We're going to start at chapter 4. There is going to be quite a bit of proofs in this chapter. So if you need to review your previous chapter's notes, it would be a wise decision. But I think you're going to find out you're going to be actually pretty good at these by the end of the chapter. You're really pretty good working with these notes. But so a lot of this chapter is all about polygons, but mostly triangles. So when we're working with these, you're going to be on top about almost everything, all right? So with this, you're going to take what you thought a little triangle was way back when, and we're going to define it correctly. We're going to make sure we have correct notation. So some of this is like, Gregerson, this seems so simple. But you're going to find out if you don't use stuff correctly, homework also can turn into really hard. All right, so let's make sure we care about these little details. They're wonderful definitions for, the quiz on Friday, because this will be on the quiz. So, things like that, make sure you know the details. All right, so we're talking about introduction to triangles. So I think it was basically the review for it. So if this isn't a review, I'm sorry. You should have had this before. But let's make sure we have every little detail now. So first of all, let's review the properties of parallel lines because they do not go away. We use them quite a bit still. All right? So go back to chapter 3. If I have parallel lines, what do I know? What do I know? So alternate interior angles are congruent. All right. What else do I know?
Exterior angles.
Oh, yeah. Alternate exterior angles, right? Yep. And corresponding angles are congruent. And what was our last one? Same side?
Supplementary.
Supplementary, right. So same side, interior angles are supplementary. Now, the moment you hear the word parallel, those should be the 4 things that go through your mind first. But remember, I can use the converse of those to prove lines parallel. So we have to be able to go both ways. But also we had things like if one line, if I have parallel lines, and if one of the line is perpendicular to the transversal, the other one's perpendicular to the transversal. So we had some very logical theorems that flowed as a result. But if you have those and their converses down, you've really got a big key of what we did, basically over half of our chapter 3 stuff. So we were on top of it. So these will come in handy. Don't forget them just because we took the test on Friday. Are you guys with me on that? Yes, sir.
Oh, no, we're going to get adjusted by standard.
No, what did I say? Probably what happened. Do you remember? Probably block. Okay, probably block. All right, so let's go talk about one of the easiest shapes in the world to work with. A what? A triangle. Now, when you were little, or when you watched Sesame Street, let's just go there, and you guys would watch Sesame, you would just say it's a shape with 3 corners, right? Okay, how about if we actually get the right definition down, okay? The correct definition is the following. It is a closed figure formed by 3 non-collinear points and 3 line segments with each point being an endpoint for 2 of the segments. And really, when you read it like that, it's very simple to see. So 3 non-collinear points. We have to have 3 line segments to connect them. That makes sense. And to make sure that they all get connected, and so we don't have 3 line segments going just to one of the points, we say, all right, each endpoint can only be for 2 of the line segments. So that's what makes it that closed shape. Now, with these, we need to know a little bit different parts for this. Every point, or every one of those endpoints you want to talk about, that's called a vertex. Plural for that is vertices. So a triangle is going to have 3 vertices. Every one of the sides, they specifically tell you, is a what? A line segment. So can I talk about length? Can I talk about midpoints of a line segment? Could I say that line segment's parallel to some other shape's side? Yeah, so there's a lot of different things that we could talk about with this. So just remember your side is going to be named as a line segment. So if you ever name a side as a line, I won't give you credit for it. So let's think notation through a little bit with these. Now, one thing I told you was always be careful with notation in this class. Because remember when you name a plane, what type of points are you supposed to use? Not collinear. Coplanar, keep going. What type of coplanar points? Non-collinear, right? So remember I said if you don't see the word plane, you could be messing up. But remember I said if you make a triangle, you make a plane. Remember we got the tripod idea? So do you see why now if you just sit there and said ABC, are you discussing a plane or are you discussing a triangle? Or are you discussing an angle? You don't know, right? So notation is huge. Now this is where math is nice, right? A lot of times it's very obvious what the notation is going to be. Well, you're going to have a triangle. So you got triangle ABC. Now, here's how you name any type of polygon. A triangle is the smallest polygon out there. You can't go any smaller. And you literally start at a point, and you either go counterclockwise or clockwise. So basically, you're playing connect the points. So in here, if I just go triangle ABC, I'm going clockwise, right? But let's just say I wanted to start at A, and I didn't want to go towards B. I could go to which one? So you have triangle ACB. Yes, Peter?
Isn't the triangle sign like a delta too?
No. A delta and a triangle are similar to two different things. Delta means you're subtracting two things. Triangle, not. No, a delta sign has it increased off to the side. There's a difference. It doesn't really matter if they're smaller or not. It's just a simple, like a delta sign actually has one of the sides thicker. So there's a difference. So it's not the same thing. So if you found out a triangle is a delta sign, nope. But here's the thing. Is A the only point you can start with? Oh no, you can start with B. And you can go clockwise with B. You can go BCA, and you can go counterclockwise if you wanted to, and go BAC. But maybe you don't like either A or B to be the one you start with. Maybe you're just an individual who likes C better. So you could go triangle CAB, or you could go triangle CBA. For that triangle alone, how many different ways I can name it? How many is that? There's 6 different ways for every triangle. So first of all, notation matters, but you also have to understand how you name a polygon. You start at one point and then you go around. Like I said, it doesn't matter if it's clockwise or counterclockwise, but remember you're literally playing connect the points. So if I said triangle ABC, like this first one right here, I start at A, that means I have to go to B, and I have to go to C, but since it's a triangle, I know where do I have to end up at? A. That's how the symbols tell you what to do. Remember the same type of idea when you talk about angles and stuff. Make sure you fill those in carefully. Guys, with me on that? All right, now there's some other things you need to know, and there's a typo in here, so if I forget to tell you guys, I think you'll catch it right away. Triangles are classified 2 different ways, by side length and by angle measurement. You've had all of these before. Did everyone hear me on this? Now you have to really know them. Okay, now you have to really know them. So let's make sure we can draw these out and write the definitions down correctly. The very first one is an equiangular triangle. What does equi mean? So they're equal what? Angles. So if you're to draw a triangle, what should you mark in your triangle? Yeah, congruent marks. Yeah, the arc marks, that's right. So I have congruent angles. So an equiangular triangle, all the angles are the same. Guys, what's the measure of those angles? Careful, it's not 45. Should be 60, right? So you just take 180 and divide it by what? 3. And so those are all 60 degrees. You have permission to use that as much as you need. Because if you know that they're each going to be 60 degrees, if I have just like a 3y in there or something like that for an angle measure, can't you just go 3y equals 16, solve for it real quick? So, but it has to be what type? Yep, equiangular, right? Now this is a typo here for the next one. So acute triangle, it says all angles are less than 90 degrees. So all the angles have to be what type of angles? Acute, so that's why they use that. So when you're thinking about that, just draw a triangle if you can. Do something like 70 degrees, let's say 60 degrees, and maybe like 50 degrees for your triangle. So they're all different ones in this case. Now, looking at that, could I also say that an equiangular triangle is acute? So are all equiangular triangles acute triangles? All right, so that they can be classified by both. So make sure you know that and you put that down in assignments. But here's my question. Are all acute triangles equiangular?
No.
No. So remember, it doesn't go both ways. So it can't be a biconditional this time, right? Really only goes one way. And then all of you have been working with these before. We've even talked about them a little bit. You have a right triangle, and it's a triangle with only one right angle. So anytime you're ever given the fact you have a right triangle, you always mark in the right angle, no matter what. Remember that? We could even say that the legs of that right triangle are perpendicular. But I mean, right triangles are pretty obvious. And then remember the obtuse one? It's just a triangle with an obtuse angle, which means it has to be greater than 90. Can I have more than one obtuse angle? No. Otherwise, it wouldn't add up to 180. Can I have more than one right angle in a triangle? No, because 90 plus 90 is 180, and I still have to get my other angle, right? So we need to make sure that we have those when you're working with it. Make sense? All right, so that's just for angles. Now, if I ask you to classify triangles by angles, please don't do it by sides. Do specifically what's being asked. So we're going to have to use what word? The R word, my friends. Make sure you do it. All right, be careful. Now, we can also go by side length, but there's only 3 for the classifications with this. And again, you've had these all before. The first one's equilateral, which means equal what? Equal sides. So all 3 sides are going to be the same. Looks really familiar to a different one, doesn't it? And we'll be able to prove it later. We'll be able to prove it later. And then, can we have just a service announcement for Mrs. Gregerson's sake? Could you please learn how to spell isosceles now? No. Some of you might kind of chuckled on that one. No, I'm not lying. This is a word we use so much. It's on ACTs, SATs. I use it like all year long with you. And for like isosceles trapezoids, isosceles, all this type of stuff. Could you learn how to spell it before you take your quiz? Also, if that's on your quiz, don't you think there's a good chance somewhere else on the quiz there's going to be the word isosceles? So could you please just make my life not miserable by trying to read your writing and actually spell it correctly? I have one request. I haven't yelled at you for, many of you are still struggling on how to spell non-complainer and complainer. Okay, we could probably correct those by now too. All right, but could we please make sure you spell isosceles correctly? Vertical, yeah, that was my other one. I had to do that one, not verticil, it was vertical. You guys have gotten better at that, so it's good. But could we please spell isosceles right? I know I'm like going a little too long on this, but trust me, it's awful. I've done this for 20 years. I've seen lots of spellings of isosceles. This is only one that works. Okay? With me? All right, yes, ma'am.
For the equilateral, since all sides are congruent, should it be equal?
They're equal in measure, so it's the same thing. Right? Equal length means congruency. Yep. All right, isosceles triangles. Here's the key word. At least, and that is key. There's a reason why I had it out there. It means at least 2 sides are congruent to each other. Which doesn't that mean, if necessary, 3 sides could be congruent to each other? Which then means all equilateral triangles are what? Isosceles. Sounds kind of familiar to like what we were talking earlier, right? But here's the thing. Are all isosceles equilateral?
No.
No. Guys, I'm going to tell you right now, isosceles triangles need to become your friends. We're going to do lots with them. So you're going to have to be really good. So remember, know the definition well. And the next one is scalene triangle. And guys, I'm just pulling off my shelf here just a little what? Scale. When a scale leans, it means it's not what? Hello, isn't that the easy way of memorizing it? Yeah, because a scalene has no sides congruent. Or no sides equal in length. So keep it easy way. Now, an easy one to draw, just because it's simple, is just draw a quick little right triangle. It's just a 3, 4, 5. You can see the different side lengths a lot easier. They're scalene. Nothing's equal. It's a leaning scale. Think of it in that sense. All right, that's really it for today's stuff. All right, so we're going to sit there and we're going to practice. Now, a lot of people really struggle because they don't take the given information and be able to go a step further with it. I don't think that's going to be you guys, but don't be surprised if I throw like factoring or something with you on this type of stuff, and I'll explain when we get to those problems. But let's go through one problem just to make me happy, to make sure we all have the notation and stuff down correctly. It says the following for here. for example 1, it says, name the following triangle in as many ways as possible. Don't forget to use correct notation. And then for part B here, it says, next name all the vertices of the triangle. And then for C here, finally name all the sides of the triangle. So basically what I'm asking is, tell me all the parts. But if you're doing this right, how many different types of triangles should you have? All right, go for it. Give me them with correct notation. Should have 6, correct? And remember, make sure you go in order, especially when we get to quadrilaterals and other shapes. It's going to be really huge that we name our points either going clockwise or counterclockwise around the figure. But vertices, well, vertices, remember, are just points. So you're just going to have your 3 points, and we're going to go D, I, G just because I can't help myself because I think that's kind of funny. Got points, Dig? Got it? Little things in life make me happy. And then for your sides, how do you name the sides? As what? As line segments. So make sure if you name the sides, you do it with the correct notation. So you have like line segment ID. I'd go to line segment DG, and then line segment GI. Notice I just went around the triangle when I named it, so I didn't skip anything.
Is it like the names where we have to name both of them? So we have to do like I and DI?
No, because remember, it doesn't matter which one first. I just said name the sides. So if you name them, you're implying that there's 4. That means 6 sides. I don't want that. I just want the 3. Okay, good stuff. Now, guys, was that really that hard? Oh, no. Yep, moving on. Now, this one, be careful. It says classify each triangle by its angle measures. Note, some triangles may belong to more than one class. So when we're talking about this, only thing I'm looking for is what? Angle measures. So am I going to talk about equilateral, isosceles, or scaling on them right now? No. We're only looking at the angles. So the first one is ABD. So this one right here. What type of triangle is that? All right, so that's an obtuse triangle. Excellent. And you guys are going to notice I abbreviate triangle all the time with the triangle symbol. We'll replace it. All right, the next one is ADC. Yeah, right here. Here's ABD. What's that measure right there? This is 100 degrees, right? One obtuse angle, it's obtuse. All right, now how about triangle ADC? This one right here. Yep, it's the right one. Do you guys see the right mark? That doesn't mean the angle's being bisected. Doesn't mean you have a right angle. So that's a right triangle. All right, and then we have triangle BCD. Well, we don't know if it's isosceles because we don't know angle measurement, right? But I do know that I have an 80-degree angle there because of my linear pair, right? So 40 plus 80 is 120. That leaves this one to be 60. What would I classify that triangle as? Yep. Use it to your advantage. Acute triangle. Excellent. All right, now let's do side lengths. So much fun with side lengths. It says first one, triangle GIJ. Triangle GIJ. What do you guys think? Yeah, it's going to be scaling. The one reason why I know that, just because even how the tick marks work, we know those two are the same. That makes it twice as long as this side, right? Yeah, so it's pretty easy. So this would be scaling triangle. Remember, this is by side lengths. Now, how about the next one? HIJ, this one off to the right. Very good. Equilateral triangle. And if it's equilateral, it's automatically also isosceles triangle, right? My S and C there. That makes, so it's also isosceles. Excellent. How about GHJ? This one right here. Yep, that one's just isosceles this time. Awesome. So remember, there can be more than one thing with this one. How do you guys feel so far? Pretty good, right? Now, the next type of problems, I've kept them pretty straightforward. However, don't be surprised if I threw like a factoring problem or something with this. Did you guys hear me on this? Factoring, very easy to put on this type of problem. Now, on the first one, it says just find the side lengths of each triangle. So I want all 3 sides measures. Okay, all 3 sides measures with this. So what would you do for the first one, guys? Zach. Now that's for angles. I'm talking sides, so I can't do it for sides. That's not a bad thought, but you gotta remember sides can't do that with angles. Otherwise, all triangles will be very boring. All right, Drew.
You put 3x minus 0.4 equal to x plus 1.
Yep. The only thing I know for certain is that these 2 sides are congruent. So I have an isosceles triangle. So I can go ahead and set them congruent to each other. So I can go 3x minus 0.4 equals x plus 1.4. So I get 2x is equal to 1.8. Guys, what's x going to equal? 0.9. Right? So now with this one, notice I'm not yelling at you to use fractions right now. Why? Because I gave you decimals to start with. All right, simple as that. But now all you have to do is just plug and chug them in. So let's do, what do you guys want to do, RP or RQ first? RP, all right, so we're going to use RP. Notice notation, no segment bar because we're talking length. So we go here 3 times 0.9 minus 0.4. So that's 2.7 minus 0.4, which is going to give us what? 2. All right, so what do I know about RQ? So it's 2.3. Do I need to plug and chug? No, it's a great way to check yourself to see if you're right. It's 2.3. And then we have PQ, 0.9 plus 0.1. That should be 1, right? Notation, notation, notation. I'll be watching, see if you're correct on these. Yes? Which one you said? RP and RQ are the same. If you only way you could have done it otherwise if you said like this. I would take that too. Does that make sense? Because RP and RQ are the same. So either way I'd do that. Okay guys, let's look at the next one. What do I know? They're all the same. It's an equilateral triangle. So I know they're all equal. Now how many equations do I need though? I need 1 equation, right? I just need 1. So here's the cool part. Does it matter which 2 sides I set equal? No. So pick 2. What 2 sides are we going to use? So ST and TU, you said? See, I wouldn't have done that. If you don't like fractions, why would you pick 2 with fractions?
Do ST and T.
But it doesn't get rid of the fractions. It doesn't get rid of it. You don't get rid of it though, unfortunately. So
Yeah, no.
I would have done this one.
Yeah, ST and TU.
Because they're equal to each other, even though I know I'm working with fractions, because guess what? You're not going to get rid of them in this problem. But at least I know I can do less with fractions on this one. Because if I do, I have 3 3/4 is equal to 5n right away. Now, when you know you're multiplying and dividing, is it a really good idea to leave it as a mixed number? No. Isn't it easy to make that an improper fraction? Isn't that going to be 15 over 4? Right? So it'd be 15 over 4. So remember that was 3 3/4. I just converted it into an improper fraction. Now if I'm dividing by 5, that's the same thing as multiplying by its what? So do you guys agree with me? 1/5 times 15 over 4 is going to equal n. I got 3/4. Is that what you guys got? All right. Now here's the cool thing. You can pick which side you want to plug it into because they're all what? All equal. So which one would you pick? Yeah, me too. I would do the one with the length of segment US. So US is going to equal 7 times 3/4. Well, guys, remember that's the same thing as 7 over what? 1. So isn't that 21 over 4? And if you leave it as 21 over 4, that's fine because literally we know US, or my other ones on here, ST and UT are all 21 over 4. Or if you're a mixed number person, it just makes you happy, 5 and what? 5 1/4? It's fractions. Did you see me shy away from it at all? You guys need to lean into those too. You guys need to be better at fractions. All right, let's do some proofs. Let's do some review. This stuff read carefully, look at your marked up diagrams carefully, right, guys? They might write givens next to it. They might actually talk about perimeter. What's perimeter?
Oh, the sides added up.
The sides added up. Maybe that has to be used for some reason. So again, redraw diagrams, mark up what you know on these. You will probably get it to come to you. Now the next ones are two proofs. I just want to see if we can review some of the concepts and stuff that you need. A lot of people, when we were doing the proof in the last class, wanted to go the long route, algebraically. Guys, I'm not asking you not to go algebraic on this next proof. It's a lot faster if you don't. But with this one here, you got to remember everything I do in class has a purpose. I want you to learn to think conditionally. There's a reason why we did logical arguments, and I keep going, if then, if then. Law of detachments is huge. But look what's given to you. Your very first given tells you what to do next. Segment BD bisects angle ABC. If I give you an angle bisector, what do you give me? Which two? Yeah, make sure you actually use your angles. That'd be 3 and 4. So my very next step is angle 3 is congruent to angle 4. That's just definition of a what? Definition of angle bisector. If you want to write that down, I will accept it. If you wrote it as a conditional statement, would I be okay? If given an angle bisector, then you get two congruent angles. Isn't that the same thing? Yeah, so we have that. So now we're good. Now I'm kind of stuck again, right? Just twiddling my thumbs, nothing else to do. So where do you go? You go to your diagram. Does anyone see any linear pairs sitting around? Yeah, 1 and 3 and what? 4 and 2. All right, so I'm going to actually put that in the same step because I don't want to write my reason more than once unless you want to look cool and have longer steps. Okay. So here I got angle 1 and angle 3 are a linear pair. And you know what? Let's do it this way. Let's say angle 1 and angle 3 and angle 2 and angle 4 are linear pairs. Does that make sense? And that's just definition of a linear pair. All right, what do you know about linear pairs? Not equal. They're supplementary. And I'm not going to go plus equals 180. I'm going to go strictly with the supplementary this time, and you guys will see where this is going in a moment. So I know angle 1 and angle 3 are supplementary. And I'm going to write this in the same step. Angle 2 and angle 4 are supplementary. And that's just linear pair what? I love linear pair theorem. We can use it either to get the equal sign or just say the word supplementary. Now guys, I'm at my end of my proof. I'm ready for my therefore statement. I want to repeat a theorem to you and see if you guys remember what it's called. If two angles are supplementary to the same angle or congruent angles, then they are congruent to each other. Do you guys, instead of having to the same angle, this time they're supplementary to what type of angles? Congruent ones. This is just the congruent supplements theorem. So therefore I know angle 1 is congruent to angle 2 by the congruent supplements theorem. That theorem is really handy. Now some people are like, doesn't it have to be there? I see a linear pair. Yeah, we just proved it. We said why it had to be there. It works out pretty good. Make sense? What do you guys think? Yes, Jacob.
I was just looking at the next proof, and there is no.
You know, just pick that J. That was a typo.
Okay.
All right, and that, in fact, he stole my thunder on this one. But change that to an LJ. If you guys wouldn't mind doing that for me, I'd really appreciate it. So here's our given. LJ is parallel to segment DK, which is a parallel to segment AP. So what should I mark on my diagram? They're all parallel, so I'm going to go all the same arrowhead on there. I'm also given the segment PL is parallel to segment AG, so I know this is true. Right, guys? Now what? I'm trying to prove angle 1 is congruent to angle 2. And this one's actually easier than it looks. Oh, I heard alternate interior angles. Is anyone going to agree with Mikey on this one? How about, you could do corresponding, but you can actually skip it. Guys, notice what line I'm not using, or line segment I'm not using. Yeah, I'm not using KD. You can, you'll just end up having like maybe 2 steps more, but it would be really easy just to ignore it this time. Because as long as I have AP is parallel to LJ, I'm okay. So let's go ahead and let's write it down because you're going to see how easy it is. Here are statements, reasons. I get segment LJ is parallel to segment DK, which is parallel to segment AP. And the nice thing is I can excuse, I don't have to use segment DK in this case. If you did, you'd be okay, but you don't need to. Because I can go straight to the fact that angle 1 is congruent to angle P. Now, why can I name an angle by 1 point? If that's the only angle at that vertex, you can. Otherwise, you have to name it more than that. But aren't those alternate interior angles? So if I have parallel lines, then alternate interior angles are congruent. So I got 1 in angle P, great. Now what else? Jason. You said angle P is congruent. Okay, I just have to write a given down first, but yes, that's correct. All right, don't I just have to put my second given first? Yeah, but Jason, that was exactly what you need to do next. All right, so we'll put it down. So I get segment PL is parallel to segment AG, so I have to have that given down. And then I'm going to do exactly what Jason told me to do. Angle P is congruent to angle 2. Again, what's the reason, guys? Alternate interior angles. Awesome. So if I have parallel lines, then alternate interior angles are congruent. Bless you. Wow. Now, guys, am I done? What steps haven't I used yet? 2 and 4, right? And so I have to do a transfer property. If I have angle P is angle 1 is congruent to angle P, and angle P is congruent to angle 2, angle 1 needs to be what? Yep. Very good. Yep. Yep. Yeah, they're not hard. Here's the reason why. You're starting to recognize them quicker. Okay? That was not meant to be a hard one. The other one was a little bit harder. But here's the thing. If you have not been reviewing your past notes, what do you need to do? Review your past notes. All right, homework's just from the textbook. And we have a quiz on Friday. Like I said, if soccer does something cool, we'll make it work. Sound good?